Hello, my name is Michael O'Reilly, and this is my lab report that covers Lab 3, which is magnetic field of a bar magnet. So to begin with the purposes of this lab, one is to find the distance dependence of the magnetic field of a bar magnet in Part A, showing the diagram on top. Then we compare the accuracy of the results of Part B, where the magnetometer and the phone is at a distance d perp on the x and the y-axis at an angle of 45 degrees above the bar magnet. We then compare the accuracy of the results to the accepted Biot-Savart law. So for the results, it's n, or the exponent of the distance dependent of the magnetic field of a bar magnet, is negative 2.01, and the magnetic dipole moment of the bar magnet that I received from Dr. Greco was around 6.67886 ampere per meters squared. The measured results are within reason of the accepted equation that we will discuss later, and will be calculated with the code. The fundamental principles used in this lab are the superposition of magnetic fields and the magnetic field of a bar magnet. So now for the procedure and initial observations. We have the orientation of the phone's magnetometer made to counteract Earth's magnetic field in the x direction. So we align the phone until Bx is close to 0, so we can ignore the Earth's magnetic field. The results would be different and inaccurate had we not done this. So for the assumptions, the magnetometer is kept in correct orientation in the lab, and the other magnetic fields besides the targeted two are deemed insignificant. And finally, the data illustrates the magnitude of the magnetic field to be increasing nonlinearly as the distance decreases. Now onto the analysis of the observations. We plot the natural log of the magnitude in the x direction and the natural log of the distance, which gives us the slope. We can see that the distance squared has an inverse relationship to the absolute value of the magnetic field, and we can use the y-intercept, which is the ln of k, and due to k being equal to mu naught over 4 pi times 2u, to find u, which is the magnitude of the magnetic moment of the magnet, which, as we mentioned earlier, is 6.67886 ampere per meter squared. Now on to the coding complement. The code on the next few slides serves the two main purposes in the lab, one being a 3D visualization of the magnetic field and distance dependence using the given equation. The other purpose is to be a comparison for our measured values for observation at 45 degrees to be expected values from the equation that is shown at the bottom of this slide. So this shows a diagram of the magnetic field of a bar magnet. We used the dipole B function at 6 various observations, which were all at a distance d from the origin around the gray bar magnet. The orange arrows shown in the diagram in the code output are the observation locations on the axis with the magnet, and the blue arrows are observation locations perpendicular to the magnet. The orange arrows should be and are in the opposite direction and twice the magnitude of the blue arrows, because that is how it is for the magnetic field of a bar magnet. So now onto the perpendicular coding results. We insert a magenta colored arrow which represents the magnetic field at 45 degrees at a distance d, which is around 0.261205 meters from the magnet. And this distance was found from the perpendicular distance that was measured in the lab, d perp, which equals 0.1847 meters. We also get a result for the magnetic field, which is shown on the second bullet point and in the code. Now onto the data comparison. The measured values for the magnetic field and the code give our similar magnitudes for the components. The tables show that there is a BZ component, but that is only due to the Earth's magnetic field, as the magnet and the magnetometer were on the same plane. So the BZ value is 0 Tesla. The results are fairly close, but differ due to human error and lab procedure. It's good that they're in the same direction and are close in magnitude for each component, as this ultimately means that the data is accurate and correct. Finally, onto the conclusion, the magnetic field of a bar magnet has an inverse relationship to the distance away from the magnet, which is roughly squared. Also, the net magnetic field is superposition of Earth's magnetic field and any applied magnetic field, such as the bar magnet. The lab procedure of measuring the magnetic field using the magnetometer in the phone with given bar magnet gives very similar results. So if the two magnets were stuck together, if those were used instead, the magnitude of the magnetic field would increase and the distance needed for a specified magnitude would decrease. Thank you very much for listening to my presentation.